Somewhere out past the edge of the sun's influence, more than 14 billion miles from where you're sitting right now, a machine built before the personal computer existed is still doing its job. It has no idea it's famous. It has no idea headlines occasionally borrow its data to suggest something eerie is happening out there in the dark. It just keeps measuring patiently the way it has for decades and sending back a signal that takes over 20 hours to reach us, traveling at the speed of light. That machine is Voyager 2. And yes, it is picking up a frequency from beyond our solar system. That part of the headline is true. But almost everything people imagine when they hear that sentence is wrong, and the real explanation is stranger, slower, and in its own way far more impressive than anything a clickbait title could capture. Before we get into what Voyager 2 has actually found, we need to slow down and be precise about what kind of frequency we're even talking about, because the word alone tends to conjure an image it doesn't deserve. This is not a radio broadcast. It is not a signal in the sense of a deliberate transmission from anywhere or anyone. Nobody working on this mission, no scientist publishing in a peer-reviewed journal, has ever suggested that something out there is calling to us. What Voyager 2 has genuinely detected is a frequency in a much more technical, much more mundane sense of the word, a specific measurable oscillation in the density of charged particles drifting through the empty-seeming space between the stars. It's being picked up by an instrument that has been quietly running on this spacecraft since before most of the people reading or watching this were even born. Once you understand what that instrument is actually doing, and why the particular frequency it detects matters as much as it does, the real story turns out to be genuinely remarkable on its own terms. It doesn't need any exaggeration bolted onto it to be worth your attention. So let's build this up properly, piece by piece, starting with the hardware responsible for all of it. The device responsible for every one of these detections is called the Plasma Wave Subsystem, almost always shortened to PWS in the scientific literature. It has been flying aboard both Voyager 1 and Voyager 2 continuously since the two spacecraft launched in the late summer of 1977, a year that, worth remembering, also gave us the first Star Wars film and disco still dominating the airwaves. Physically, the PWS is a 16-channel, step-frequency receiver working in tandem with a separate low-frequency waveform receiver. It doesn't have its own dedicated antenna, array. Instead, it shares the same two long V-shaped antennas mounted on each spacecraft that another onboard instrument, the Planetary Radio Astronomy Experiment, also relies on. Think of those antennas less like a satellite dish pointed at a target and more like an extraordinarily sensitive pair of ears, tuned to catch faint disturbances in the electromagnetic environment surrounding the spacecraft from whatever direction they happen to arrive. The basic job of the PWS, in plain language, is to detect oscillations in the density of charged particles, specifically electrons, moving through the plasma that surrounds the spacecraft at any given moment. That plasma might be sitting comfortably inside the heliosphere, the vast bubble of solar wind the sun blows outward in every direction. Or it might be sitting in what we call true interstellar space, the region beyond that bubble where the material drifting around no longer originated from our own sun at all. For most of the mission's working life, this instrument mainly recorded activity tied to the planets it flew past and the outer structure of the heliosphere itself. Useful, but not exactly the instrument's claim to fame. It's only in the years since both spacecraft physically crossed out of the sun's protective bubble that the PWS has quietly become one of the single most valuable pieces of equipment still functioning on either machine. And the reason for that shift is almost poetic. The instrument turned out to be capable of something nobody had originally designed it to do. It could measure the density of interstellar space itself, directly, from a distance, that still strains the imagination even when you say the number out loud. 14 billion miles. Not 14 billion feet, 14 billion miles, and an instrument built in the 1970s is still doing precision physics from out there. To understand why a frequency reading can tell you anything at all about how much material is floating around in a given patch of space, you need one basic piece of plasma physics, and it's genuinely elegant once it clicks. A plasma is simply a gas made up of charged particles rather than neutral atoms, electrons and ions drifting around instead of the neutral molecules that make up the air you're breathing right now. When a plasma gets disturbed, even slightly, its electrons don't just settle back into place quietly. They overshoot, they swing back, they oscillate back and forth at a very specific natural frequency, in much the same way a plucked guitar string vibrates at a specific pitch determined by its tension and length. Here's the key detail. That oscillation frequency depends directly and predictably on how dense the plasma actually is. Denser plasma, more electrons packed into a given volume, oscillates at a higher frequency. Thinner, more sparse plasma oscillates at a lower one. This relationship isn't a rough approximation or a rule of thumb. It's described by a precise mathematical formula that plasma physicists have understood for the better part of a century. What that means in practice is genuinely powerful. If you can measure the frequency at which a patch of plasma is oscillating, you can calculate its electron density with real precision, without ever physically touching the material, without scooping up a sample, without sending a probe directly into it. You just listen to the pitch, so to speak, and you can work backward to figure out exactly how much stuff is producing that pitch. That is precisely what the plasma wave subsystem does, over and over, year after year. It listens for what scientists call electron plasma oscillations. And every single time it catches one, researchers back on Earth can take that specific frequency, run it through the formula, and calculate exactly how dense the surrounding interstellar plasma was at that particular moment. This has become, by the researchers' own description, their primary, and quite possibly their only, method for directly determining local plasma densities out in true interstellar space. There is no other instrument currently operating anywhere in the universe that can do this job from where Voyager sits. Here's something that tends to surprise people. This entire capability wasn't planned. It was discovered essentially by accident, more than 10 years before either spacecraft had even reached the boundary of the heliosphere. Rewind to July 1992. Both Voyager spacecraft were still deep within the outer reaches of the solar system at that point, nowhere close to interstellar space yet. And both of them began picking up strong radio waves sitting in a narrow band between 2 and 3 kilohertz. Not an enormous signal by any means, but a clear, consistent one that stood out against the background noise. Don Gurnett, the physicist at the University of Iowa who led much of the research built around this instrument, and his colleagues went to work tracing the origin of those waves. What they found was that the signal traced back to 6 large solar flares that had erupted on the sun's surface more than a full year earlier. The plasma ejected during those flares had been traveling outward the entire time, and it eventually struck the heliopause, the outer boundary of the sun's influence, causing electrons there to oscillate and emit exactly the kind of radio waves that Voyager's instruments were now picking up, more than a year after the eruptions that caused them, expected for the interstellar medium beyond the solar system. It was an early, indirect clue, a whisper of what conditions were like beyond the edge, detected years before either spacecraft would physically arrive there to confirm it directly. That 1992 detection also produced one of the more memorable lines in the entire history of this research program, one that says a lot about how consistently this mission has managed to upend the community's own expectations. Going into the crossing, scientists broadly expected that the magnetic field beyond the heliosphere would point in a noticeably different direction compared to the magnetic field inside it. A clean, predictable signature that researchers hoped would help confirm exactly when a spacecraft had crossed the boundary from solar territory into true interstellar space. It didn't happen that way at all. Stamatios Krimigas, one of the senior researchers on the mission, later reflected on that mismatch between prediction and reality with a line that's been quoted ever since, essentially observing that nature simply hadn't read the theorists' papers and evidently didn't know it was supposed to change the magnetic field's direction at the boundary. It's a wry, almost affectionate way of describing a genuine scientific puzzle. To this day, researchers still don't have a fully settled explanation for why the magnetic field outside the heliosphere lines up so closely with the one inside it. That open question traces its lineage directly back to those very first plasma wave detections from 1992, and it remains one of the more interesting unresolved threads in heliophysics. Voyager 1 was the first of the 2 spacecraft to actually cross the heliopause, doing so in August 2012, at a distance of roughly 121.6 astronomical units from the Sun. 1 astronomical unit is the average distance from the Earth to the Sun, so we're talking about a spacecraft that had traveled well over 100 times farther from the Sun than we are. Confirming that crossing turned out to be far more complicated than researchers had hoped, and the reason comes down to bad luck decades in the making. Voyager 1's plasma science instrument, the instrument specifically designed to directly measure the speed and density of surrounding plasma, had already failed back in 1980, more than 3 decades before the spacecraft ever reached the heliopause. Without that direct measurement tool available, scientists had no choice but to lean heavily on the plasma wave subsystem instead, the instrument nobody had originally built for exactly this purpose. On April 9, 2013, roughly 8 months after the crossing had actually occurred, Voyager 1's plasma wave instrument began detecting locally generated electron plasma oscillations at a frequency of about 2.6 kilohertz. Running that number through the density formula produced an electron density of roughly 0.08 particles per cubic centimeter, a figure remarkably close to what scientists had theoretically expected for the interstellar medium. That single frequency measurement, arriving months after the actual event, became one of the clearest and most direct pieces of evidence confirming that Voyager 1 really had left the solar system behind. And it happened precisely because an instrument never designed for this exact job stepped up when the purpose-built instrument had already failed. Voyager 2 followed its twin out into interstellar space 6 years later, crossing its own section of the heliopause on September 5, 2018, at a somewhat closer distance of about 119 astronomical units. Unlike Voyager 1, Voyager 2 still had a fully functioning plasma science instrument at the moment of its crossing, which gave researchers direct, real-time confirmation of the sudden environmental changes, happening as the spacecraft moved from one region of space into another. You'd think that might make the plasma wave subsystem somewhat redundant on this particular crossing, but it turned out to be just as valuable as it had been for Voyager 1, arguably even more so. The reason is simple but powerful. Having two independent spacecraft cross the heliopause at two completely different locations meant scientists could, for the first time, compare plasma frequency measurements gathered from two separate points along the boundary, rather than relying on a single dataset collected from just one location. That comparison is where things start to get genuinely interesting. Comparing the two spacecraft's measurements produced one of the more quietly significant findings to come out of this entire body of research. Something researchers now describe as a radial density gradient in the very local interstellar medium. Earlier, simpler models of interstellar space had generally assumed that the plasma out there sat at roughly one uniform density everywhere beyond the heliopause, a flat, featureless sea of thin gas. The frequency, measurements gathered by both spacecraft's plasma wave instruments, told a different story entirely. They revealed that density actually climbs steadily the farther outward you travel from the heliopause. It's a genuine gradient, not a flat value. According to combined analysis of both instruments' data, that climb happens in two distinct phases. Initially, the density increases quite rapidly, by almost a factor of 2 within roughly the first 5 astronomical units after each spacecraft first began detecting plasma oscillations beyond the boundary. After that steep initial rise, the density continues increasing, but far more gradually, eventually reaching approximately 0.12 particles per cubic centimeter by around 160 astronomical units out from the Sun. Think about what that actually represents. Using nothing more than the precise pitch of plasma oscillations, picked up by 2 decades-old radio receivers built with 1970s electronics, scientists mapped out how interstellar plasma density genuinely varies with distance immediately beyond our solar system's edge. No purely theoretical model could have produced a picture this detailed, this confidently, without that real data feeding into it. More recent analysis has sharpened that picture even further. A study published in the Astrophysical Journal Letters, examining Voyager 1's electron density measurements out beyond 160 astronomical units, highlighted a more refined detection technique available on the spacecraft's plasma wave instrument. Beyond simply catching occasional plasma oscillation events triggered by solar storms, which happen irregularly and depend entirely on when the Sun decides to erupt, the instrument's high-resolution wideband receiver is also capable of detecting something called a quasi-thermal noise line, sitting precisely at the electron plasma frequency. This technique allows for considerably more precise and more continuous density measurements than simply waiting around for the next solar-triggered event to arrive. Using that more refined method, researchers identified a pressure pulse around day 146 of 2020 at a distance of roughly 149 astronomical units from the Sun. Since that pulse, the measured density has remained relatively steady, holding at approximately 0 to 147 particles per cubic centimeter based on the most recent observations available. Some researchers involved in that analysis have suggested this steady, elevated reading might indicate that Voyager 1 has reached a broad density peak, or possibly even entered an entirely new physical regime within the interstellar medium altogether. If that interpretation holds up under continued observation, it would be a genuinely significant milestone, marking the first time either spacecraft has settled into a stable, plateau density reading after years of steadily climbing measurements. Now we get to the part of this story that's most likely to get exaggerated in a headline, so it's worth being especially careful and precise here. A team of researchers at Cornell University, digging more closely into Voyager 1's plasma wave data, discovered a class of very weak, narrowband plasma wave emissions that persisted continuously in the data starting sometime in 2017. This was fundamentally different from the discrete solar-triggered plasma oscillation events that had, up to that point, been the primary source of every density measurement discussed so far. Those earlier detections were sporadic by nature, tied to specific, identifiable solar storms that had reached the heliopause months after erupting, producing a burst of data and then falling silent again until the next event. This newly identified signal was different. It simply kept running steadily in the background, allowing for a continuously sampled measurement of interstellar plasma density spanning roughly 10 astronomical units, with individual measurements spaced only about 0.03 of an astronomical unit apart. That's a level of continuous, fine-grained sampling that nothing else in this entire body of research had previously come close to achieving. Analyzing that steady stream of data, researchers found small-scale density fluctuations on the order of individual astronomical units that trace out genuine turbulence within the interstellar medium itself. Subtle ripples filling in the gaps between the larger, more dramatic plasma oscillation events that solar storms occasionally trigger. That persistent, continuous signal is what researchers and subsequently the media eventually nicknamed the interstellar hum. And it deserves one more round of clarification because this really is the piece of the story most likely to get twisted into something it isn't. It is not a broadcast. It is not evidence of anything intelligent anywhere. It is simply the electromagnetic signature of ordinary charged particles in interstellar plasma, oscillating at their own natural frequency, a frequency that happens to sit within a narrow enough band and stay steady enough over time that Voyager's decades-old receiver can pick it out clearly against the background noise. Researchers involved in identifying this signal reached for a genuinely evocative comparison to describe it. Imagine a very sensitive microphone picking out the faint, continuous hiss of steady rainfall, with the occasional dramatic plasma oscillation triggered by a solar storm representing a sudden clap of thunder cutting through that rainfall, before everything settles back into that same faint, continuous background hum once the storm passes. Step back for a second and consider just how unexpected this entire category of finding was to the scientific community going into this mission. Researchers studying the interstellar medium prior to these detections largely assumed that the space beyond our solar system would turn out to be relatively smooth and quiet, a comparatively uneventful, roughly uniform sea of extremely thin plasma with not much texture or variation to speak of. What both spacecraft's plasma wave instruments have instead revealed, frequency reading by frequency reading, over years of patient listening, is a region of space considerably more textured and dynamic than that original assumption ever accounted for. There's a measurable density gradient stretching outward from the heliopause. There's small-scale turbulence rippling through that density on astronomical unit scales. And underneath all of it runs a persistent, if extremely faint, background hum, continuous and unbroken, humming along regardless of what else is happening around it. There's one more genuinely dramatic category of detection worth covering in detail, because it loops directly back to those very first 1992 radio wave observations that kicked off this entire line of research in the first place. When the Sun experiences a coronal mass ejection, violently hurling a massive cloud of magnetized plasma outward from its surface, that eruption generates an enormous pressure wave. That wave eventually travels all the way out through the solar system and slams into the interstellar plasma sitting beyond the heliopause. When it collides with the surrounding interstellar medium, it creates a genuine shock wave, and that shock wave causes the ionized gas out there to resonate, essentially ringing like a bell, at frequencies both Voyager spacecraft's plasma wave instruments can actually detect and measure from over 14 billion miles away. Researchers have documented multiple events of exactly this kind since both spacecraft crossed into interstellar space. One of the more detailed recent analyses, examining data gathered across a region researchers now call the outer heliosheath, found that Voyager 1 has observed two major shocks in two separate pressure fronts driven by solar activity since crossing the heliopause, while Voyager 2 has recorded two pressure fronts and one shock of its own. Every one of those events was detected and characterized specifically through the frequency of the plasma oscillations it triggered. What makes these shockwave detections so scientifically valuable is that each one hands researchers on Earth an entirely independent way to cross-check the plasma density readings coming from every other method available. Denser plasma rings at a noticeably higher frequency than sparser plasma does when struck by one of these pressure waves, functioning almost like a bell made of interstellar gas, one that changes its pitch depending on exactly how much material it's actually made of. That cross-confirmation matters enormously in a field where researchers can never send a follow-up mission back out to double-check a single measurement. Every data point has to be extracted as precisely as possible from a signal that already traveled 14 billion miles before it ever reached an instrument built with 1970s technology. It's worth situating all of this within the broader, ongoing story of exactly where both spacecraft actually are at this moment and how much longer this kind of frequency detection can realistically continue. According to the most recent modeling of the region both spacecraft are currently passing through, Voyager 1 and Voyager 2 have now reached heliocentric distances of approximately 172 and 143 astronomical units, respectively. Both are still within a region researchers call the outer heliosheath, a transitional zone where interstellar plasma flow remains significantly decelerated and heated by ongoing compression. Both spacecraft are still gradually approaching an expected maximum in plasma and neutral atom density. projected to occur somewhere between 200 and 250 astronomical units from the Sun, according to recent kinetic models of this region. In other words, and this is genuinely worth sitting with for a moment, even after everything both spacecraft have already detected, neither one has yet reached what researchers consider the truly undisturbed, quiet depths of interstellar space. The frequency measurements keep coming precisely because both spacecraft are still passing through an active, still evolving transitional zone, one that continues to produce genuinely new data with every additional astronomical unit either machine manages to cross. None of this ongoing detection work comes free, and it's worth acknowledging the increasingly narrow path both spacecraft are walking just to keep any of it going at all. Both Voyager 1 and Voyager 2 are powered by radioisotope thermoelectric generators, devices that convert heat produced by the natural radioactive decay of plutonium into usable electricity. There's no way to refuel that process, no way to slow it down, and no way to reverse it. That power source has been losing roughly 4 watts of available output every single year since launch, a steady, predictable decline baked into the physics of radioactive decay itself. To manage that shrinking power budget, NASA has had to shut down instrument after instrument on both spacecraft over the decades. By early 2026, each spacecraft had already been reduced to just 3 working science instruments. Then, an unexpected power drop on Voyager 1 that February forced engineers to sacrifice yet another instrument that April, leaving both spacecraft down to just 2 functioning instruments apiece. Here's the detail that says everything about how much this particular data actually matters to the scientific community. In both cases, the 2 instruments the mission team specifically chose to keep running, ahead of every other option on the table, are the magnetometer and the plasma wave subsystem, the exact instrument responsible for every single frequency detection described throughout. This entire story. NASA has explicitly stated its intention to keep operating those 2 instruments on Voyager 2 for the foreseeable future, precisely because the data they continue to provide about the structure of interstellar space remains genuinely irreplaceable. It's being gathered from a vantage point no other spacecraft currently in existence, or even currently planned, will be able to reach for decades, if ever. Step back and look at the full arc of this story. It starts with a somewhat accidental radio wave detection in 1992, triggered by solar flares that had erupted more than a year earlier and only became visible once their plasma finally reached the heliopause. It runs all the way through to a modern, continuously updated picture of interstellar density, gradients, small-scale plasma turbulence rippling through the dark, and shock waves that keep ringing for years after the storm that first triggered them. Every part of that picture was extracted from one basic physical principle. A plasma's electron density can be calculated directly from the frequency at which its electrons naturally oscillate. And every one of these findings came from an instrument that was never specifically designed to measure interstellar space in the first place, repurposed by researchers who only recognized what it was truly capable of after both spacecraft had already traveled far enough to test it directly against a region of the universe nobody had ever been able to sample up close before. So when you come across a headline claiming Voyager 2 is picking up a frequency from outside our solar system, understand that in the narrow, technical, entirely real sense, that claim is absolutely true. It's been true in one form or another since July 1992, and it remains true today, with both spacecraft's plasma wave subsystems continuing to listen continuously for exactly the kind of faint, narrowband oscillations that first revealed the density, the turbulence, and the still ringing shock waves scattered throughout the space between the stars. What it doesn't mean, and what no credible research coming out of this mission has ever actually claimed, is that anything or anyone out there is transmitting to us. What it actually means is far quieter and, honestly, a lot more moving. 2 machines, built with less computing power than a modern digital watch, launched during a decade when disco was still on the radio, or still listening carefully enough, decades later, to hear the universe's own quiet, ordinary hum. And they're still finding new, genuinely surprising things buried within it, every single time researchers take the time to sit down and listen closely enough to what these 2 old machines are actually picking up, 14 billion miles from home.